Every single time you send an email or stream a video, you're setting off this incredible, invisible journey. So today, we're going to follow a single piece of your data as it travels across the globe at nearly the speed of light.
So think about it. You snap a photo of your dog, you hit send, and boom, it's on your friend's screen. Feels instant, right? But here's the thing. That file doesn't just teleport. So how does it actually get there?
Well, the very first thing your computer does is it basically turns into a digital post office. It takes that big photo file and in a flash chops it up into thousands of tiny, easy-to-handle pieces.
And these little pieces, they're the heroes of our story. They're called data packets. Think about it like this. If you wanted to mail a 1,000-page book, would you try to ship it in one giant, heavy box? Probably not. It'd be way easier and a lot more reliable to just mail it one page at a time. And that's exactly what we're doing with our data.
Okay, so each and every one of those tiny packets is built just like a little digital postcard. And don't get bogged down by all the technical terms on this slide. The main thing to know is that it's got 3 key parts: a section for the address, the actual message itself, and a little quality check at the end. In tech speak, that's the header, the payload, and the trailer.
So, the header, that's your address label. It's got the sender's and receiver's IP addresses, which are basically the digital version of a street address. But here's the really crucial part. It also has a sequence number. Think of it like page 1 of 1,000. This is how the computer on the other end knows exactly how to put the photo back together in the right order.
Next up, the payload. This is the postcard's message. It's the actual data, a tiny, tiny slice of that photograph you're sending. So each packet is just carrying one small piece of a much larger puzzle. And finally, we have the trailer. This is the quality check. It does 2 things. It signals, hey, this is the end of the packet, and it includes this really clever bit of math called a cyclic redundancy check, or CRC. Basically, it's a way to make sure the packet didn't get scrambled along the way. If the math doesn't check out when it arrives, the receiving computer just says, no, that one's no good, send it again.
All right, so our photo is now chopped up into thousands of perfectly addressed, perfectly checked little packets. And now we release them into the wild, chaotic world of the internet.
So let's look at this diagram. As the packets leave your computer, let's call it computer A, they all start out in a perfectly straight, neat line. 1, 2, 3, 4, 5. Seems simple enough, right?
Well, here's where it gets really interesting. The internet isn't some single straight road. It's this massive tangled web of routes and routers. And each packet, all on its own, finds the absolute fastest path available in that exact millisecond. So if one route is jammed with traffic, a packet just goes, okay, I'll take a different way.
And the result? Well, you can see it right here. Our neat little line of packets arrives at the destination, computer B, completely jumbled up. Packet 4 might show up first, then packet 1, then 5. It looks like total anarchy, but it's actually an incredibly smart system called packet switching. And this is the very reason the internet is so darned resilient.
So why on earth would we use a system that looks so messy? Well, because it's incredibly efficient. Instead of hogging one single connection for your entire file, your packets can just find another route if something's down or busy. The only tiny drawback? That little delay at the end while the destination computer uses those sequence numbers we talked about to put everything back in the right order.
Okay, so for all of this sending and receiving and re-requesting of packets to actually work, computers need to follow some basic rules of the road for how they talk to each other.
And there are basically 3 main modes. First, you've got simplex. That's a one-way street. Think of your computer sending a document to your printer. The data only goes in one direction. Then there's half duplex, which is like a walkie-talkie. You can talk and you can listen, but you can't do both at the same time. And finally, there's full duplex. That's your standard phone call, where both people can talk and listen simultaneously. And yeah, most of our internet connections today are full duplex.
All right, so beyond just the rules of who can talk and when, we also have to think about the actual physical highways that data travels on. And there are 2 main types here.
This slide shows them perfectly. On the left, you've got serial transmission. You can think of this like a single-lane country road, where all the bits of data have to travel in one single file line. Then on the right, you have parallel transmission. This is like a massive multi-lane superhighway, where a bunch of bits can all travel at the very same time.
So you're probably thinking, the superhighway is always better, right? More lanes, faster speeds, what's not to love? Well, not necessarily. As you can see from this chart, there are trade-offs. Sure, parallel is faster, but it's also more expensive because it needs more wires.
And it only really works well over short distances before the data starts getting out of sync or skewed. Serial, on the other hand, might be a bit slower, but it's way more reliable over long distances.
So how does all this abstract theory apply to something you probably use every single day? Let's talk about the humble USB cable.
Yeah, I mean, just take a look at the cable that's plugged into your keyboard or charging your phone right now. Which one do you think it is? Is it that single-lane country road or the big multi-lane superhighway?
Well, the clue is right there in the name. It's the Universal Serial Bus. That S actually stands for serial. And it makes perfect sense, right? For a universal connector that needs to be cheap, simple, and super reliable, the serial method was the absolute perfect choice.
And that's really why USB completely took over the world. It was so much more than just a data cable. It was plug and play, you didn't need to install a bunch of drivers, it became a true industry standard, it could actually power your devices, and it was backward compatible. Plus, you couldn't plug it in the wrong way, well, at least not without trying 3 times first.
Of course, the next step in that evolution is USB-C. It finally solved the plugging in problem for good by being reversible. But more than that, it dramatically cranked up the power and data speeds, letting it do everything from charging your laptop to driving a 4K monitor.
And it's all built on those same fundamental principles we've been talking about, breaking data into packets and sending them reliably using serial transmission. It's really set to become the one cable to rule them all.
So when you think about it, from the organized chaos of packet switching that makes our internet so robust, all the way to the humble serial cable connecting everything on our desk, the journey of our data is just a masterpiece of engineering. It really makes you wonder, what's the next big problem that a new standard will come along to solve? Thanks for tuning in.